Iran's new long-range anti-ship ballistic missile, a truly game-changer weapon. Iran has successfully tested an anti-ship ballistic missile capable of hitting mobile targets at a range of up to 1,500 kilometers. This was stated by the Chief of Staff of the Iranian Armed Forces, Major General Mohammad Bagheri, quote, "By producing this type of missile, Iran has become one of the 3 countries in the world capable of manufacturing them," said Bagheri during a meeting with young soldiers from elite units, specifying that the missile's speed is Mach 8, and it has recently been successfully tested several times. Bagheri then added, "By owning this type of missile, we will create significant security in our surrounding seas, up to a radius of more than 1,000 kilometers." Earlier, Iran unveiled an anti-ship ballistic missile called the Persian Gulf. The missile has a range of 300 kilometers. It is a single-stage solid-propellant ballistic missile equipped with a high-explosive or a cluster warhead and uses a combination of guidance systems, namely inertial navigation and electro-optical homing, which enables the missile to detect and lock on to the target. Other short-range solid-fuel more advanced anti-ship ballistic missiles, such as the Hormuz missile in 2 variants, with a different homing system, namely a passive anti-radiation sensor, have also been fielded by Iran to steer the warhead toward the source of radar emissions on warships. According to General Hajizadeh, commander of Aerospace Force of the Islamic Revolutionary Guard Corps, IRGC, Hormuz 1 can destroy radars on an aircraft carrier, a Patriot site on land, or a detector radar site. A film released by AIMA Media shows the Persian Gulf missile hitting a fixed ship on the sea, which underlines that the maneuverability of this missile is rather limited. However, since it is a short-range and supersonic missile, it takes less time to reach the target at a distance of 200 to 300 kilometers. Therefore, the target will not have much time to change its location significantly, and certainly not at full speed, since it will most likely not know that it is being targeted or, if radar systems are available, will not be aware of the missile until it has already traveled a large part of the distance. Therefore, Persian Gulf missile with its optical guidance can still detect and destroy even a moving target at that distance. However, at ranges of several hundred kilometers and more than 1,000 kilometers, especially 2,000 kilometers, the movement of the target during the flight time is considerable, and depending on the speed of the ship, the displacement during the missile's flight can exceed 10 kilometers, posing a serious challenge to accurate target detection. According to Major General Bagheri, Iran is now able to engage moving targets at a range of up to 1,500 kilometers using a new anti-ship ballistic missile with a speed of Mach 8. This means that the still unknown missile will fly in the hypersonic regime, which significantly shortens the flight time to the target and reduces the displacement range of the target at sea. According to some rumors, this new anti-ship ballistic missile, which is already in the phase of mass production, could be the naval version of the previously presented Castle Breaker missile with a range of 1,450 kilometers. However, the question arises as to how Iran managed to acquire this unique capability? A capability that very few countries in the world possess. The answer is that Iran has achieved a stable kill chain by establishing a set of advanced capabilities and data fusion. What does this mean? For a ballistic missile to hit a mobile target at 1,000 kilometers or more, Iran has to know where that target is located, with a high degree of accuracy. That's complicated when the target, such as a carrier strike group, is moving at up to 55 kilometers per hour. For the weapon to be effective, such a geographic fix must be updated constantly. To locate a carrier initially, Iran could use its mobile and static over-the-horizon (OTH) radars, which can search out more than 1,000 kilometers, noting that the geographic accuracy of long-range OTH radars can be off by as much as a few kilometers. But this low accuracy can be greatly improved through advanced signal processing and the use of artificial intelligence. In any case, it will be enough to get an early warning and have a working basis for the collection of further accurate data to finally solve the targeting problem. In the following, airborne radars, and a large number of network drones are likely to be used for the accurate localization of the enemy, as Iran does not currently have space-based advanced and network detection sensors such as SAR satellites. Therefore, a large number of network drones launched from Iranian shores or a drone carrier, which Iran is currently building, is the best available option to provide continuous surveillance. In any case, the network drones will be equipped with long and medium-range electro-optical devices operating in passive mode and passive radiation sensors for signal collection emitted by a carrier group, as in the Shahed 149 drone and the US-based RQ-170 Shahed drones, which have a low radar cross-section, reducing the likelihood of interception. Beyond the American RQ-170-based Shahed drone series has been produced in large numbers and reach a range of up to 4,400 kilometers, significantly increasing Iran's surveillance and targeting capabilities over the Indian Ocean. The Shahed 171, which is a full-scale model of the US RQ-170, can even reach the U.S. strategic base at Diego Garcia in the Indian Ocean if it is on a suicide mission. Long-range reconnaissance aircraft or attack submarines could also pinpoint a carrier, if they were operating in the right area. However, Iran lacks both of these capabilities, and generally in a time of conflict, a patrol airplane or submarine attempting to get close to a carrier shielded by its E-2C early warning airplanes, FA-18 interceptors, and an anti-submarine screen of subs and destroyers might not succeed. Therefore, building a stable and robust drone network is the key to solving the target problem. After overcoming this initial difficulty, finding the target by the missile warhead without any external assistance is the next big challenge. Naturally, the types of terminal seeker that Iran might use are also important. One type is an electro-optical seeker, which uses the spectral signature of a target to identify it. Unfortunately, atmospheric conditions and hours of darkness can often get in the way. An infrared seeker can overcome those shortcomings by using a target's heat signature for identification. However, even the best infrared seeker is open to spoofing with technology that either masks or mimics heat radiation. Relatively little is publicly known about the Iranian Maneuverable Reentry Vehicle, MARV, warheads targeting and homing sensors. However, it is likely the MARV will conduct an initial target search using SAR during the midcourse phase, meaning that the warhead, while in the space, already performs the task of target finding by using SAR technology. The warhead speed of Mach 8 allows for a larger synthetic aperture, which increases accuracy. It also makes up for the relatively small seeker size. A SAR uses the velocity of the platform carrying it to achieve far higher cross-range resolution than the laws of physics would otherwise allow. Since radar pulses travel at the speed of light, a traditional short-wavelength radar can generally resolve a target's range to within a few hundred feet by measuring the time between the radar's transmission and its reception of the target's radar reflection. The radar's cross-range resolution, though, is limited by the radar beam's width at the range of the target. A radar beam spreads as it propagates in direct proportion to its transmit beam width. For example, a radar with a 2-degree beam width would have an approximately 22 km wide beam at 640 km from the radar. This means a target 640 km away could be located up to 11 km left or right of the beam's centerline. Wide beam width also means that the radar cannot easily distinguish between multiple target reflections in the beam at that range, meaning a single ship as opposed to large swells on the ocean's surface. The only way for a traditional radar to decrease beam width and increase cross-range resolution is to increase the size of the radar's antenna or antennas. For high cross-range resolution at distant ranges, the necessary antenna size becomes impractical. A SAR, in contrast, uses a mathematical shortcut to attain high cross-range resolution. A SAR knows how far the platform it is mounted on, for instance, a satellite, has traveled laterally in a given amount of time. By taking this lateral motion into account, it can integrate the pulse-to-pulse measurements of the target's range along with the relative motion-induced Doppler shifts in the reflected radar pulse frequency. This allows the SAR to increase its cross-range resolution as if had a much larger antenna, hence, a synthetic aperture, and a correspondingly narrowed beam width. With this increased cross-range resolution, a SAR conducting wide-area search can resolve smaller targets from background clutter and/or can discriminate smaller features on a single target. Furthermore, a highly sensitive SAR transmitting at a sufficiently short wavelength can be used to image a target's real-world shape. This image, if refined enough, can be used by the SAR's control processor or a human operator to determine whether the target is a warship, a merchant ship, a landform, a decoy, etc. A very capable SAR can even distinguish between different warship classes. These discrimination capabilities would obviously make deception much harder for the defender. The SAR search would be necessary to correct for detection and surveillance error, an area of uncertainty regarding the target's location at the time of the anti-ship ballistic missile launch. The MARV would likely conduct an exo-atmospheric maneuver to adjust its aim point based on this updated target location. The MARV warhead would have a separate sensor suite for terminal homing. Terminal sensors could include a millimeter wave radar, an RF direction finding sensor, an imaging laser, an infrared sensor, and/or an electro-optical sensor or a combination of them. The missile-borne radar can even have a SAR and usual radar modes. It is reasonable to believe that any millimeter wave radar contained within the terminal suite would have a search mode sensitive enough to detect aircraft carriers, amphibious warships, supply ships, cruisers, and destroyers against an ocean background. With sufficiently high resolution, the terminal radar might also be capable of inverse synthetic aperture radar, ISAR, imaging to support final aim point adjustments, as well as discriminate the targeted ship from unsophisticated decoys. Inverse synthetic aperture radar, ISAR, uses the same relative motion principle as SAR to achieve higher cross-range resolution than the radar antenna's physical size would otherwise permit. While SAR uses the radar platform *s velocity relative to a target to artificially increase cross-range resolution, ISAR uses the target's angular motion relative to the radar for the same purpose. An ISAR-equipped reconnaissance airplane or missile flying towards a target will only see the target's radar reflection grow in intensity as it approaches. This closure will not induce much relative angular motion. Ocean swells, however, will induce a warship to roll slightly from side to side. Since the ISAR knows its transmit wavelength, it can integrate the slight relative angular motion-induced Doppler shifts in its pulses reflections off the target to calculate the target's cross-range position with greater precision. ISAR assumes that the target exhibits angular motion generally independent of, and typically unknown to, the radar. Therefore, it differentiates it from SAR that takes a static target scene. It provides a way to produce high-quality images of ships by use of their angular motion. The main idea is to create an image using the phase difference from the object's angular movement. If the ISAR uses a suitably short wavelength and has sufficient sensitivity and discrimination capabilities, it can image the target by integrating the positions of the individual shapes that constitute the target. The other sensors in the suite would likely help with target discrimination as well as provide a measure of redundancy in the event one or more sensors failed to operate or were effectively jammed. It is important to note that if a RF direction finding sensor is included in the suite, it might also be able to help support the MARV warhead's midcourse phase aim point adjustment maneuvers based on the targeted battle force shipboard radar emissions. Considering the MARV warhead's hypersonic speed upon atmospheric re-entry, it will need to slow its descent considerably to provide the terminal sensors the tens of seconds they need to search for, identify, and track the targeted ship. A pre-programmed speed control maneuver by the MARV at a 25 to 50 km altitude to support terminal sensors search as well as interceptor missile evasion is likely. In addition to the MARV's evasive maneuvers, the Iranian anti-ship ballistic missile could employ penetration aids such as faster-burning rocket motors, chaff clouds, active electronic warfare systems, decoy objects, and measures aimed at reducing the warhead's observable signatures. The MARV's payload could be a deck-penetrating unitary high-explosive, submunitions for destroying carrier aircraft parked on deck, or a warship's topside sensors and communications antennas, or high-power microwave, HPM, devices for neutralizing unshielded sensors and communications systems. Iran's new missile with a range of 1,500 kilometers could threaten a carrier well outside the combat radius of carrier aircraft without in-flight refueling. Therefore, this new anti-ship ballistic missile is a key element in Iran's strategy of developing an anti-access, area denial, A2AD, capability. Iran's naval doctrine suggests that U.S. Navy aircraft carriers' land attack capabilities make them highest priority targets for Iran's anti-ship ballistic missiles, ASBM. However, they are not the only U.S. naval targets. Carriers' dependence on at-sea logistical replenishment make supply ships desirable targets, and that strikes conducted during underway replenishment operations offers the chance of neutralizing carriers and supply ships simultaneously. Iran's doctrine also highlights the importance of preventing adversaries from deploying new forces into the West Asian theater and East Mediterranean Sea or resupplying forces already in the theater. Iranian strategists additionally observe that the U.S. Navy's Aegis BMD-capable cruisers and destroyers could potentially reduce the effectiveness of Iran's land attack medium-range ballistic missile strikes in West Asia. Sea-based missile defense patrol stations might be ASBM targets early in a war to either destroy or force these U.S. Navy combatants to expend their ballistic missile defense interceptor missile inventories. However, some important points should be mentioned here, because attacking a mobile target at sea is anything but simple and a routine operation. Indeed, it is a challenging task and involves a series of complex operations that must proceed smoothly and robustly, because a simple way to counter the Iranian A2AD approach would certainly be for the Americans to disrupt the Iranian kill chain. To succeed in attacking U.S. forces, Iran's surveillance systems must locate U.S. forces, its communications networks must relay targeting information to weapons launchers, weapons must be launched. Launching a ballistic missile takes some time, although Iran has significantly shortened the launch time in recent years, and then Iran must home in on U.S. forces. Each of these steps is vulnerable to interdiction or disruption, and because each step must work, U.S. forces can focus on the weakest links in the chain, not each and every one. Americans could disrupt surveillance systems with electromagnetic or cyber attacks, using electronic warfare and jamming as well as cyber weapons to prevent Iran's long-range radars and drones from seeing U.S. carriers. That disrupts the first link in Iran's kill chain, namely finding the target. Once that link is broken, Iran will have trouble completing the rest of the chain and attacking U.S. carrier group. Airborne or surface-based jammers could prevent over-the-horizon radars from finding a carrier strike group. Therefore, long-range tactical and/or fixed but highly protected radars with electronic countermeasures and electronic countermeasures capability are of immense importance in preventing them from being jammed by enemy jammers and destroyed by cruise missiles. The first wave of U.S. attacks on critical Iranian infrastructures will certainly be carried out by large numbers of cruise missiles. Electronics, cyber, or kinetic weapons could also be employed to blind and destroy Iran's airborne radars and drones, which would be needed to pinpoint a moving target. To prevent this, it is imperative that Iran build an integrated air defense network off its coast. By deploying Shahid Soleimani corvette ships with long-range air defense systems and other air defense systems, such as KH-3, Iran is already trying to reduce the impact of a potential attack on its critical assets such as radars and drone network as well as other critical infrastructures. It will be of great importance to position a number of heavily armed warships with long-range cruise missiles several hundred kilometers off the Iranian coast to establish a line or multiple lines of defense against U.S. kinetic and electronic warfare operations. Iran has already begun building more Shahid Soleimani-class ships and is currently working hard to build drone carriers. In recent years, Iran has also made some progress in building submarines, and more work is underway. Destroyers escorting the carrier could also deploy off-board radar reflective decoys that could deceive the missile into aiming at a balloon floating over empty ocean. To prevent this, the missile warhead will probably have to be equipped with multiple sensors and artificial intelligence. In the terminal stage, U.S. Navy destroyers could employ the Aegis SM-3 ballistic missile defense system to protect the carrier. This system is among the most advanced air defense systems with a high direct kill rate. Therefore, the attacking missile must be on an unpredictable trajectory and may have to use penetration aids and various other means mentioned earlier to defeat such an advanced system. To increase the hit probability, and thus increase the chance of finding the target and penetrating the sophisticated U.S. anti-ballistic shield, a large number of missiles can be fired at a carrier group more or less simultaneously. Iran could also deploy long-range loitering anti-ship drones, such as the famous Shahid-136 with a range of 2,000 kilometers, to either track and destroy the escorting warships or at least deplete U.S. munitions and disrupt U.S. jamming and kinetic operations against Iran's capabilities and assets. Therefore, to thwart U.S. defensive and offensive tactics, Iran must build an extensive and robust kill chain as well as defensive and offensive weapons against a range of electronic, cyber, kinetic attacks, and deception tactics. It is very likely that an attack on a U.S. aircraft carrier group will require a significant number of Iranian defensive and offensive weapons such as radars, drones, warships, cruise missiles, offshore air defenses, and other weapons to be included in the operation. Hitting a moving target on the sea is not just a simple launch of an anti-ship ballistic missile from Iranian soil with a seeker that finds the target. Only in a robust multidimensional framework will the Iranian attack succeed. Time will tell, but Iran has already set the stage for a major and unprecedented strike against U.S. forces at sea, the likes of which has never seen before. This is Neutrino.Science.Defense channel. Thanks for watching and see you next time.